page of quotes and that in practical terms, Martin Gardner may be one of the most influential writers of the 20th century, given his popularization of lots of concepts in math and science. So this book looks like this in the inside is kind of a cartoon. It actually was meant to accompany a film strip, which is another piece of technology that's even older than CDs. You probably have to ask your grandparents what a film strip is, but it's basically that cartoon. And many of the things in this book are stories and paradoxes and ideas that were taken from other people. But actually, this particular story, I think, is original to him. So I wanted to credit him with the story. And I wanted to go through this story because it emphasizes some really interesting things about information and how we think about information and the physical aspect of information. So there's just a few panels, and it's a sort of alien invasion story, a friendly alien type. And the idea is that there's some alien, Dr. Zeta, a scientist from another galaxy, comes to visit Earth, and he meets this American scientist named Herman. And he wants to know, this alien scientist, like about the Earth and what goes on here. And so Herman says, well, why don't you take a set of encyclopedias? So this is back in the day where instead of having things on the internet like Wikipedia, we had physical books. And so it's like, well, here, take the set of encyclopedias. It tells you lots of information about all sorts of things. And the alien scientist said, that's great, but I can't carry that much stuff. It's too big, right? However, I can encode the entire encyclopedia on this metal rod with one mark on the rod. And the American scientist asked, well, how can you possibly do that? How can all the information, all these books, 30 volumes worth of information be encoded with just one mark on one rod? And he says, okay, here's what we do. We're going to make a code, right? And so for every symbol that's in the book, so all the letters and numbers in capital, lowercase, of which there are a few hundred thousand, I'm going to assign a number from 1 to 999, right? And so every letter and symbol and character has a number to it. And it's always going to be 3 digits. And so if I want to spell a word like cat, I can put the three-digit codes together, 003 for C, 001 for A, 020 for T. And that'll be the numerical encoding of this word. And then I'm going to take the encyclopedias and use my powerful pocket computer. I'm going to scan the encyclopedia, and I'm going to basically turn all that text and symbols and things like that into one big number, a gigantic, super long number. And then in front of that number, 500, 501, 503, 027, etc., I'm going to put a decimal point, which turns this giant number into some number between 0 and 1. So it's just some fraction. And then I'm going to take this stick that I have, and I'm going to make a mark on it, and that's going to cut the stick into 2 pieces. The first piece has length A, and the second piece is length B. And I'm going to cut it so accurately that the ratio of the length A to length B is going to be some number that's less than 1, and it's going to be exactly 0.501503027, etc., so that it spits back out that huge number, which has all this information about the entire contents of the encyclopedias. And then when I get to my home planet, I'm just going to take that rod, figure out what that number is, put it back into my computer, run the reverse program, and spit out the encyclopedia. So there I can store all the information in all these encyclopedias on one mark on one rod. So there's a question of like, can you do this? Like, does this actually happen? And the first step is to encode information in numbers. Of course, since these books were written many decades ago, we do more and more of this. So this is a standard way of encoding information in numbers. And it's called a Unicode, UTF-8. And every single number is assigned a 4-character string. So E is 0045. You can actually see that each symbol here, so J004A, the A basically stands for 11. So the symbols actually go 0 through 9, and it goes A, B, C, D, E, F. So it actually goes up to 16. And the reason for that is that 16 is 4 bits of information. So I can use 4 switches, on-off switches, transistors that go on and off, other ways of encoding information to encode one of these characters here, and then 4 of them make up the string that gives you the particular letter or number, ampersand, symbol, whatever. And this is basically all that the entire internet is, right? So if I go back to this Wikipedia page about Martin Gardner, the first thing to realize is that the page you see is actually just a code that's on the right here. And this is HTML. It's a standard way to program a web page. And that kind of code you may have play it around with yourself or know about. But you can sort of read it, and in fact, this sentence I mentioned before is directly written in the code. But there's also other symbols telling you like when to highlight things and put a link to another web page and stuff like that is all embedded in here. And then you take that code and all these symbols which encode the web page, and you turn each one of these into one of these Unicode numbers. And so there's just a series of characters that are 0 to 9 or A, B, C, D, or E. Each one is 4 bits of information. And then you can take those 4 bits and turn them into some other number if you like. But it's just one big long number for this one web page. And of course, the whole internet is just more and more web pages with more and more numbers. And so you could take the entire Wikipedia or the entire internet and just turn it all into one big long number. It's essentially already been done. We don't need a pocket computer to do that. So then it gets to the second stage of this idea, which is a single number, right, which is just between 0 and 1, can encode unlimited information, right? If you actually know one of these numbers between 0 and 1, then I can get all this information just like with this mark on a rod that the alien scientists had. So how do we actually do that physically? Well, physical quantities are often expressed using real numbers. So let me give you some idea, like distance, right? So in the particular story, it was a ratio, not a distance, but you could have cut the rod so that it was exactly cut at 0.50150302703, etc. meters, right? And that would be the exact distance between the end of the rod and the mark. Or you could have stored it in some angle, right? That same number, but some radians, or in the mass of an object. Maybe you have an object which is exactly 0.501.503, etc. kilograms, right? Or something moving at some particular speed, right? Or energy, or electrical resistance, right? So there's all different possible physical quantities, and in principle, if you can make some object have the property of having this value of any of these physical quantities and read that out, then you can do this trick about encoding as much information as you want in that physical object. So here's the question: can you encode unlimited information in a physical quantity? So let me give you another example of that, right? Which is if you have, let's say, a pencil or pen on the table or desk in front of you, one thing you could do is you can send a message and with it to somebody else by basically pointing it in one direction. So you could say, well, if I point it up, my answer to the question is yes. If I point it down, the answer is no. And so you've encoded your answer to the question or some information. This is one bit of information in this physical object. But you could go further than that because you say, well, actually, the pencil can point other directions, up and down. It could point, 10 degrees this way or minus 13 degrees the other way. So I could actually encode a single letter of information by pointing in a particular direction, right? So I just say, every few degrees or so is a different letter, and I place carefully, a little more carefully than I had to with the yes, no message, what direction my pencil is. And then somebody can read which direction it's pointing in and know whether my message was A, B, C, D, E, F, up to Z. And of course, you can keep going with a smaller and smaller angle, right? So, or discrepancy. So if you take, for example, a particular angle, which is like half a radian, 0.501503 radians, and say, well, let's tilt the pencil to be exactly that angle, then we can encode this super long number that has all the information in the encyclopedia in it, or all the information on the internet in it, just by the particular orientation that this object is sitting at. Let me give you one other scheme, because you might think about, I want to transmit information from one place to another. So here's a scheme where you say, okay, at one end, I've got a person who's got a light, and they've got a dimmer switch, which they can make the light turn it off. That we call that 0, or they can turn it all the way on to some brightness, and we'll call that 1. And somewhere else, there's another person who can see the light, and they can measure the relative brightness that they see, whether it's off or all the way on, and they've got a light meter for doing it. And so if this person wants to send a message, what they can do is they could just turn it off or on. That would send a sort of binary signal, like yes or no type of message. But they could also dim it to whatever degree of brightness they want between off and on. And so they could tune it to be not all the way on, but 0.50150302703, etc. fraction on, a little over 50% on. And then the person at the other end could read that with a meter and see this full long number and get that information from just seeing the single light, which could contain, again, all the information on the internet. And so you could send all the information on the internet at the speed of light using this scheme. So I'm going to pause here. That I hope I've made the question clear. Do you think it is possible to encode unlimited information in a physical quantity? And I think there's three possible answers you could have. So one could be, yeah, take any physical quantity, the distance, the mass, the angle, any of them, you could do this trick. Or you might say, actually, I think some of them you can do that with, and some of them it won't work with. Or you could say, actually, for none of them could you encode unlimited information. So, and if there's people can put their answer in the chat. I think I can't actually see people at the moment, so I'll stop sharing for a second. If people want to vote what they like, all right, most people coming in so far are into B so far. So which was for some of them, none. Some people are no, nothing. Some people say nothing. So it looks at mostly B's and C's so far. Nobody's yet for A. Okay, good. Let me pause there because I can't see everybody while I'm screen sharing. Are there any other questions people have while I have it pause for a moment?
He had said asking about his understanding of your encoding schemes. Way back up there. I told him I thought it was basically correct. And AJ chimed in as well. You encode information in numbers, we use binary to transmit the information, and that's basically the internet.
Yeah, that's basically.
And I said, yes, that's basically it. Simplified, but yes.
Good. Okay.
AJ pointed out this how encryption, at least factor encryption, works.
So let me go back and I'll share my screen again. And let's see whether there's an answer to this question, right? So there's a reasonable difference of opinion about, but most people are saying B or C. All right, so let's see. Okay, so if you answered B or C, or A or B, yes, I think a lot of people answered B, right? There's good money to be made, right? Because right now that 2 terabyte hard disk I showed you, which can contain a few thousands of compact disks on it, sells for $120 on Amazon, right? So your price is roughly $50-$60 per terabyte of information. So if you can come up with a device that stores unlimited information, right, you can essentially charge unlimited money for that right now. So if you believe that's the case, that's a possible career path, is developing that further. However, if you said no, none of them, then there must be some fundamental physical limit on encoding information for every possible type of quantity you could think of: mass and velocity and energy and resistance and brightness and all these things. So my main claim in this talk is that this is the answer to the question. That C is the answer. That if there's a fundamental limit, right, then there must be some rules governing why things are limited informationally speaking. And so the claim is that all physical objects must be governed by fundamental rules that limit information. It's a different way of thinking about rules of physics. Usually when you learn rules of physics, it's things are sort of in different positions in space and time. They're moving through space and time, and you want to figure out how they move through space and time, and they have different properties. But this is a sort of way of approaching the physical world as an informational world, as objects containing information. And this would be like a kind of axiom almost, saying okay, our starting axiom is to say that you can't encode infinite information in a finite physical object in front. And so that must be kind of a rule. And my further claim is that we think we know what these rules are. These rules are quantum mechanics. But one way of looking at what quantum mechanics is, what quantum science is as a theory that basically limits information, that shows that no matter what physical situation you're in, there is always going to be a limit. And you can't actually do this infinite information encoding, unlimited information encoding trick. So let me give you an example of where that fails quantum mechanically. So let's go back to this scheme with the brightness. So what would actually happen if you tried this? Well, you could set up this exactly the way I had it, where there's sort of an off and an on, not bright and brightest possible. And you could have a meter which could read that. But if you say, I really want to know the exact fraction of brightness I'm seeing to a really good precision, you'd want a more and more sensitive meter. And if you make a more and more sensitive meter, light meter, what you find is you don't just get a continuous flow of energy that gives you a reading. What you get is little spikes of energy, right? Little spikes of light energy, which are quanta of light energy, also known as photons. And so in the middle here is a trace from an oscilloscope, which is reading voltage, which is basically energy per electric charge per time. And you see something like this, which you just get little spikes. So the little spikes, depending on the type of light you're using, they might all have the same energy or roughly the same energy. And they will come in such a way that if you set this at, let's say, a half brightness, so let's say the total brightness is getting 1 joule of energy every second, and you want to set it to get roughly half a joule of energy per second, you're going to get all these photons coming in that add up to roughly a half a joule. But it's never going to be exactly a half. It's only averaging over a long time. You get closer and closer to exactly half or exactly this number. So, you can set it so, in principle, it's spitting out exactly this much energy, fraction of energy on average. But it comes in a spiky form where to actually read that off, you need to average for a long, long period of time. And the longer you average, the more you'll know this number. But you have to average for longer and longer periods of time to get more and more digits of number. And to get unlimited information, you have to average for an unlimited amount of time. And it's because of the quantum nature of light that you're limited in this scheme of transmitting, unlimited information in just a single flash of light. Because light doesn't actually physically work that way, right? If light did physically work that way, then you could do it. But quantum mechanics puts this limit on it. So what about this example of a pencil that can point in a desk different directions? And in principle, we said you could point this any angle, and that angle could tell you all the information you want. Let me make this even more extreme, because you could really use anything with any sort of orientation to it. And so rather than use a pencil, if you want to shrink things down into as small a package as possible so we can take the information to college as easily as we'd like, let me use something else small that has an orientation, and that's an electron. Right? So an electron has a few sort of standard properties. The two that get talked about most is that every electron's got the same mass, and the other is that every electron has the same electric charge, right? And there's the values of mass or charge. But an electron also has a magnetic property. It's basically like a tiny little magnet, right? And it's got a strength of its magnetic field it creates, so it's got a particular magnetic moment. And so one sort of simple way of thinking about the electron's magnetic properties is as kind of a little bar magnet, right? And that little bar magnet you can tilt, right? You can tilt in different directions. Now, this isn't the full story, because as we'll figure out, it's a quantum mechanically governed property like everything else. But that's a good starting point. And the reason why things are magnetic, like how does an iron refrigerator magnet work, is that we've lined up a lot of the electrons in that material to all point the same direction. And each one of those is a little magnet, and collectively they just make a bigger magnet. So if you actually want to line up a magnet, like an electron, all you do is just take a bigger magnet. And the magnet, the North Pole is attracted to the South Pole with a bigger magnet, and then you can rotate around your bigger magnet. And so if I wanted to rotate a pencil, I do that by hand. But if I want to rotate an electron, I just need a big magnet applied to an electron, and I need to rotate my big magnet so that the little electron magnet can point in that direction. And in fact, we do just that all the time, although the most common way of doing this is aligning protons on electrons. But that's what an MRI machine is, right? The big donut that you slide the person into is just a big magnet designed to align the magnetic moment of all the protons in a person's body, particularly in the hydrogen atoms in their body, up in the same direction, and use that as a non-invasive imaging technique. Okay, so again, this scheme was as follows. Let's try to encode this number not in a single mark on a rod, but in a single orientation of a single electron. So we're going to rotate our electron to exactly this angle, such that, let's say in this case, its fraction of the total 360-degree circles is, 0.501, 503, 027, et cetera, whatever information we want to encode. So this is another physical scheme. In principle, it seems like it could work, and we could store all the world's information on a single electron. Right? You don't even, a whole rod is overkill. A single electron will do. But again, quantum mechanics is going to limit this. And how it limits this is that we have to, is not so much in the preparation of it. Everything I've told you so far, you could in principle do to as good a precision as you like, given a large enough magnet to orient your electron. But the problem is in reading out which state you're in, right? Which direction is oriented. So quantum mechanics says that if you want to measure the direction of an electron's magnetic orientation, you have to choose an axis along which to measure. And when you choose the axis along which to measure, then you perform a measurement, and the measurement only gives you two answers. Either the North Pole goes one way, and the South Pole the other, or it's flipped. So there are, of course, infinitely many different ways you could orient this magnet. And there's infinitely many axes you could measure the magnet along and say, what's it doing in this direction? Is it going north up or north down? Right? And you could rotate around that dotted line however you like. And but whenever you do this measurement, you always find you get what's called a quantized answer. You don't get any possible angle. You just get a kind of yes or no answer. Like it's going one way or it's going the other way. So you can encode an infinite amount of information in the magnet direction, right? But decoding, you only get out two possibilities, right? Which is again back to just one bit of information. So this is what a quantum bit is. So a quantum bit is some object that has a continuum of infinitely many possible states, right? And in our case, you think about a little magnet, which you could rotate in infinitely many different directions, just like the pencil you could rotate in infinitely many directions, just the electron you could rotate in infinitely many directions. So there's infinitely many electron states, and each of those states corresponds to, let's say, like a point on a circle, right? The different direction that it points in. And so there's infinitely many points in a circle, and so this encoding trick for encoding information can in principle work. And when you make a measurement, and there's infinitely many possible measurements, and in this scheme, I'm going to measure along this up-down axis, you only observe two possible states of measurement. Once you make a measurement of the state, it jumps to either be the top state or the bottom state. So I have here a little animation, and I'll actually I think I can do this, make sure I can see the chat at the same time. Let me see if I can see it again. I'll put a link in the chat there if you want to play around with it yourself. Let me share screen again, and I'll show you a little video of what this looks like. All right. So I can play this video. Yeah. So what I can do is I can basically put my state in whatever direction I like. And then I can measure it. And whenever I measure it, that state jumps to either be at the top or at the bottom, right? I can also choose different measurements, different axes to measure along, right? So I can rotate that axis to make different measurements. But whenever I measure, it always goes to one of the two endpoints of the axis. And what you'll notice, the key thing that quantum mechanics does is it answers the question, well, when I measure it, where does it go? Does it go to the top or the bottom? And down here below, it tells you the percentage chance of getting each outcome. And the percentage chance is actually very easy to figure out geometrically. And that's what essentially the poster talks a lot about, which is how to do that just using geometry. So if you watch this video, there's a chance of getting a blue state or a red state, whatever the orientation. The blue state is just, the percentage chance is just whatever the length of the blue section of the diameter is, right? So you choose a measurement axis that's a diameter, and the blue part of the axis, that fraction gives the percentage, and the rest of it, the red part, gives the fraction of getting the other state. And so this is an example of a quantum algorithm. You can use, the sort of fancy quantum mechanics symbols and stuff like that to do the same problem, but you can also use geometry to do the same problem as well. And this is the rules of quantum mechanics. It basically says, okay, we're going to come up with a way of specifying all these possible states, infinitely many of them, all these possible measurements, and then tell you what is the percent chance of getting different outcomes to different measurements for any possible state and any possible measurement. That's all quantum mechanics does. So what that means, so this is an example of this quantum bit, right? For any physical object that when you measure it, you get one or two possible outcomes. In quantum mechanics, it's a quantum bit. It's always going to be the case in quantum mechanics that if you can get two outcomes, there's infinitely many states, and it's always going to be the case that there's infinitely many measurements that you could in principle do. Right? Note that a quantum bit can be used as a bit, right? So if we had an electron, we could use that electron just as a bit. We could say, instead of using infinitely many possible states, let's just have the state at the top pointing up be one state, 0, sending a message A, and the state at the bottom, 1, sending a message B. And then we'll always measure along the up-down axis, and we'll either get 0 or 1, which is exactly how you use a regular bit. But the thing about this particular object is that it seems like we might be able to do better informationally speaking. Okay? Can a qubit be used to send more information than just 1 bit? So let's think about a possible scheme. So suppose you have 2 people here and they want to send a message from one to the other, and one of them's got an electron, right? And they can agree on what their encoding scheme is and measurement scheme. And they say, well, look, I have this single electron, and instead of encoding, I know I can encode a bit of information, but what about 2 bits of information, right? So 2 bits of information, there's 4 possible measurements. So if each bit is 0 or 1, and I have 2 of them, I could have 0, 0, 0, 1, 1, 0, 1, 1, and those might send 4 messages, A, B, C, or D. But now I have this physical object, and physically speaking, I can orient that however I like, right? So I can use a big magnet to make it point up or to the right or down to the left, and I can encode 4 different messages, right? And so I can encode A, C, B, and D in those 4 different states, and then you can send that to the other person. And they can then read off what the state is and figure out which of the 4 messages it is. So in principle, it seems like this should work to send 4 bits of information with a single electron. But again, this problem is about the measurement. Right? Because when the person at the other end gets it, they can't tell what state it's in until they make a measurement. So they have to choose some axis to measure along, and then they have to make a measurement, and they're going to get only 1 bit of information out, a sort of yes or no answer. So let's take an example. All right? So suppose they get the message, and they say, okay, I'm going to measure along the up-down axis. And I get A. I get this up. So then the question is, oh, okay, I measured was essentially like along this up-down axis. I got it was the up state. So was the message A? Well, the answer is no. Because if the message were C or D, there would have been some chance for those states to turn into A. Right? There's a probability that C or D could go to A. In this case, the probability is 50%. So if the message was really C, and you made this measurement, there's a 50% chance of getting the state at the bottom B, and a 50% chance of getting A. So it could have been the case the message was C, and they measured up, down, and they got A. And the same story is true for D. So all we've done is, but this single measurement, we just narrowed down that it's definitely not B. It couldn't have been B. But it could be A, it could be C, or it could be D. So you're like, well, I didn't quite get the message. I narrowed it down somewhat. Maybe you send the message again, right? Send the same qubit again. And you're like, well, let me measure left, right this time. And maybe you get C. Maybe you get the one on the right. Right? Well, again, getting C means you ruled out D's. So now you know it's not B or D. Right? But you still can only say, well, it could have been A or it could have been B. I'm not sure, because when I measured left, right, if it really was A, there was some chance when it was A, it would jump to B. Right? So even though we sent 2 quantum bits now, we actually haven't even communicated 2 bits of information. Now, if it's a different scheme, you could have communicated 2 bits of information with 2 qubits. But it's when people realize this sort of dimly, they were like, well, it doesn't seem like there's much advantage here. So even though there's infinitely many states that you could prepare something in, and infinitely many measurements, because there's still only 2 possible outcomes, this quantum bit is no better than a bit. So the history of this field is kind of interesting, which is that in the 1920s is when quantum mechanics was developed. So last year, 2025, was basically the 100-year birthday celebration for quantum mechanics. The United Nations declared actually the entire year the International Year of Quantum as a mark of that celebration. So I put up here a picture. This is a picture of one of the people who was a significant contributor to the development of quantum mechanics, Werner Heisenberg, a name you may have heard. If you don't know about him historically, there's some chance that this show from, 10 years ago or so, which is pretty popular and still available on lots of streaming services, Breaking Bad, where the main character named himself Heisenberg, that was a sort of, popular entry of this name into culture. So that was in the 1920s. And it's really in the next decade, the 1930s, when general theories of how computation, informational processing works were developed. And I call this classical computation because they were just thinking about bits. They weren't thinking about quantum bits, right? They were just thinking about on-off switches. So a figure that you may have heard of from that is Alan Turing. A sort of general classical computer is called a Turing machine. Again, in popular culture, it's about 10 to 15 years ago, there was a movie that came out with Benedict Cumberbatch playing Alan Turing. And then finally in the 1940s, a sort of general theory of classical information was developed. So the idea of this problem of like, well, how much information can you encode in a physical object and send from one place to another? And the main figure behind that was a guy named Claude Shannon. There's been no popular movies made about Claude Shannon that I know of, but you probably know of this AI chatbot called Claude, which is named after Claude Shannon. So these were the kind of ingredients which was necessary to have to consider the idea that maybe a quantum bit could be used in some way that was better than classical bits. But nobody, even with these tools floating around, thought of any schemes to do so for kind of the reasons we've just investigated until the 1980s and 1990s. So it took 50 years after all the ingredients were there for people to sort of make this realization. And it's a nice example where, sometimes discoveries are only made just at the moment when such technology is available to make them. But there are definitely times when there are sort of ideas floating around there that could be synthesized and thought of, but people have a kind of block about the possibility of even happening, and they've kind of ruled it out, roughly speaking, to think, it's not possible. But only when people kind of revisited some aspects of quantum mechanics and understood them more deeply did they realize that, actually, we could use quantum bits in schemes that are better than bits. So in principle, I'd love to walk you through one of these schemes in detail, but even the simplest sort of algorithms for doing this are kind of complicated. But I just wanted to mention one example of the type of thing that people realized in actually the 1990s that you could do. And this is called Grover's search algorithm, right? So it's in the story, we had the idea of a computer running numbers. And of course, every time you turn a number into something else or do something like run a search, there's computational costs to doing that. If you're sending a message from one place to another, every bit you send might cost energy, it takes time. If you're running a search, every time you do a query and hit enter, there's some energy cost to that, there's some time cost to that. So this is a sort of simple example of a search, which is, suppose you have a list of 100 messages, maybe 100 different characters, right? And you want to find one particular message, let's say A, on that list. So somewhere in the list of 100 characters, there's an A. Maybe it's in the 3rd position, maybe it's the 99th position, maybe it's the 53rd position. And the question is, where is this message you're searching for among this list, right? So it's sort of finding a needle in a haystack type situation. Okay? So a classical search would be as follows. What you do is you say, well, let me run a program that says, is the first letter A? Yes or no? No. Is the second letter A? Yes or no? No, right? Each one of those is a bit of information, right? Each one of those queries takes energy and time. And it goes to the list, and maybe it's lucky and A is in the first slot, maybe it's unlucky and A is in the last slot. But on average, it's going to take you about 50 bits worth of queries to find where the A is, right? So that's 50 bits of cost, informational cost, to do this search, of computational cost to do this search. So this algorithm developed by Grover in the mid-1990s basically said, if we had the same sort of machine that could do these queries, but instead of encoding information in bits, we encode it in quantum bits. And the key thing about encoding in quantum bits is, again, not just having one bit, because one bit doesn't value much, but having multiple bits that are all tied together, which gives you even more possible states. So a single quantum bit actually, in full detail, you could tell the exact state with 3 real numbers. But 2 quantum bits, you actually can tell the exact state with 15 real numbers. So as you get to more and more bits, there are more and more numbers, each of these in principle infinite, that you can encode. And so you need to use multiple bits. And but if you use multiple quantum bits, then you could do a search process. And the key about the search process, the hardest part, is setting up the search in just the right way that you make particular measurements on your system, because you have this choice of infinitely many measurements. It's not like the regular classical search query where you're just asking a question, is the first letter A? Is the second letter A? Is the third letter A? You can ask all sorts of questions of these qubits that have this encoded information about the list. And so what they found is that on average with a quantum search, it takes 10 qubit measurements to find the message you're looking for, right? So instead of needing 50 operations, you need 10 operations on average. And it's a probabilistic outcome. So quantum mechanics is always probabilities. So it's not guaranteed in 10, but it's just on average, if we do this type of search, just like the classical search, on average, it's going to be about 10 qubit queries. And the general rule is if your list has n messages, so I have n be 100 here, a classical search is going to take you about half that. If you've got 1 million messages, it's going to take you 500,000 queries. But the quantum version of this takes the square root of that n. So for 1 million queries, it's only 1,000 qubits worth of informational processing. And as you can see, as the numbers get larger and larger, the advantage of the qubits gets bigger and bigger. So it was this type of algorithm people first discovered in the 80s and 1990s that led people to think about, oh, we actually have a computational advantages to using quantum states and quantum measurements. And then the question becomes, well, states of what? What physical systems do you want to use? And the answer is you can use almost anything in principle, right? Since everything is governed by the rules of quantum mechanics, right? You can take any physical object and think about different schemes and different types of measurements you might make, whether it's sort of energy or current or brightness or things like that. So there's a sort of wide open field of possible different architectures, physical architectures for building quantum computers. If you search quantum computer, you may find a few ones that are sort of in the lead at the moment of having like kind of the most reliable qubits. But at the present moment, we're still at the stage where 100 qubits is about roughly the order of magnitude, or 1,000 qubits. Not all of which are totally reliable that people can build into computers, but nobody actually knows at the present moment whether you can make a really useful quantum computer, how many bits you can make into the quantum computer, and even what physical system is going to be the best system to make it. So that's an active area of research right now, and you guys are all heading into this world where that type of question has become very interesting to lots of people because of the computational advantages that quantum mechanics has. But underlying it is this really interesting thing about nature, whether you care about computation or information storage or not, or practical questions, that there are limits to information, and that quantum mechanics is the rules that govern those limits. So that's what I want my message for you guys, and I'm happy to take further questions or go back to the chat, which I couldn't see given the talk, and try to run through there. So I don't know if Ariana or Lynn have been.
Yeah, so there's some really good questions in the chat that I wasn't even going to try to answer. So I just scroll up from the bottom to where you posted in your web page where you can do the
okay.
Yeah, and then there's a very interesting discussion.
Simplified binary encryption works. Yeah, so you wouldn't have to use binary. It's just sort of it's the easiest way of doing it. As you may know, it was a big invention in the mid 20th century to have these very fast, very low energy cost switches called transistors that we've been able to make smaller and smaller. And the two states that exist in, 0 and 1, on and off. You could come up with a system where you have a physical object that has 3 states, a classical computer with 3 states, but it basically works out to be kind of the same thing. Let's see. C answer. So Sid's first question about, you can encode the entire information in the electron. If you were given the same encoding of an electron again and again and again, right? You could keep measuring it again and again and again, and you would get closer and closer. You get more digits to that number, right? Just like the scheme with the light, where if you measure the brightness, the longer you average those photons coming in, the better sense you have of what that number is. But you're sort of gradually over time getting a number, and you need more and more photons or more and more electrons. So it doesn't give you any obvious advantage to send information that way. So in some sense, it's a question of whether information is lost or not. There are ways of quantifying information, as one of the contributions that Claude Shannon did was a sort of metric for like quantify the physical information. And if people talk about quantum states, they will talk about the information contained in quantum states. And that's the field of quantum information. So a quantum bit actually, depending on how it's prepared and depending your knowledge about it, will have a maximum of basically a bit of information, right? So it can have from anywhere from basically no bits of information to 1 bit of information. But that doesn't really tell you the whole story, because the whole story is that there's kind of this infinite information in there. It's just you can only extract out 1 bit of information from 1 qubit. So this thing about complete content. So there's some comment about the qubit sort of denaturing over time. People say the word is used to sometimes decoherence, right? So as you could imagine, one problem is if you orient something in a very precise direction, right, then like a little bit of wind comes along and the table gets jiggled and it like moves a little bit. And that same problem that happens with quantum bits of them being very sensitive to the environment. It depends what you make your quantum bits out of. Some quantum bits are pretty insensitive to the environment. They're very robust, and some are very sensitive to the environments. But there's kind of this interesting trade-off where essentially, the larger the bit is, physically speaking, and this is a rough scheme. It's not always true. The more sensitive it is to the environment, and the smaller the bit is, the less sensitive it is to the environment. But it's easier at the moment to make larger qubits. Yeah, and so this thing about the observer, right? So the person who sent the message knows what state it's in, exactly the state they prepared it in, so you can prepare it exactly. But the person who receives the message, right, when you make this measurement, what state it was in, you've lost that information. So from that person's perspective, when they make this measurement and they say, okay, was it up or down, and they get up, they would never, in principle, be able to recover what state it was in before they made that measurement. All they know is it definitely wasn't down. It was unlikely that it was pointing most of the way down. It was more likely it was pointing closer to up. But they can never reconstruct that. Now, somebody else may have known that information. There's another really interesting limit worth mentioning that was not discovered until the 1980s, which is, if you're given a quantum bit in some state, one thing you might want to do, let's say it's an electron in some state, is take another electron and copy the information of the electron you're given onto the second one. And so that's called basically copying or cloning, right? And you do that all the time. Like you take a piece of paper, you put it in a photocopier, you press copy, you make a copy of it. You don't have to look at what the piece of paper says, but you make a copy. But there is a no-go theorem, a thing that's forbidden by quantum mechanics, of taking an electron in one state, or a particular state, that you don't know what it's in, and making another duplicate of it. You cannot do that. It's against the rules of physics. So it's a no-cloning theorem. What you can do, interestingly, is I can take an electron in a known state and another electron that I have, and take this state and put it on to make this state into that state. But I always do that at the cost of destroying the first state, right? So I can take it from this state, this electron being this state and this state being whatever, and then destroy the state and make this one into the original state. And so this is used in schemes like quantum teleportation, right? I can take information about the physical state of something over here, destroy that, and it pops over here, as long as I have the stuff, as long as I have an electron over here and an electron over there. So there are these interesting schemes of transferring information. So in addition to quantum computation, sort of quantum information transit, signal processing, and quantum encryption is another field in which knowing the rules of quantum information really allows you to do things that you wouldn't be able to do with classical bits. Other question. So somebody asked about Heisenberg uncertainty principle. So with it was a question about the orientation as an example of the uncertainty principle. Yeah, so it's an example of you're saying is this electron up or down, right? Well, if the electron's pointing this way, right, to the right, it's not up or down. So the answer to the question, is it up or down, it doesn't have a definite answer, right? You're uncertain about whether it's up or down. It's not really correct to say that it's up or down or not up or not down. It's essentially, in this case, it's a state pointing to the right. Now, sometimes you can specify the state pointing to the right as being a kind of combination of up or down. And this is known as a superposition. This is another term that gets used sometimes in discussions of quantum mechanics. So a state to the right is a kind of combination of up or down, and that's what a state is, but it's just a state pointing to the right. And so what you're uncertain of is you're uncertain of the answer to the question, is it up or down, right? You're certain that where it's pointing to the right. But you can not answer the question, is it up or down, until you measure whether it's up or down, and then, now it's up or it's down. And now, once it's up, you're okay, now I'm certain about whether it's up, but now you have a new uncertainty, because now you can ask the question, well, is it left or right? And again, it could be either. You measure whether it's left or right, you could get this, you could get that. It's uncertain. So in the orientation of things like in electrons, you can have certainty about one direction, but that always introduces uncertainty about other directions. And so for a physical object like this, you're always saying, yeah, I know which way it's pointing. It's definitely pointing up or pointing down or pointing left or pointing right, or whatever. But you always are always measuring orientations of quantum objects, forcing it to be in one state. But then you're going to ask the question, okay, I know that its main magnetic moment is this way, but what about the magnetic properties in this direction? And there is some uncertainty about the magnetic properties in this direction, which then you can measure in this direction and find oh yeah, it's pointing that way. But now you're uncertain about this direction. So that uncertainty principle is in this story as well. So, and the uncertainty in this case is essentially in pairs, as mentioned. It's between angle and angular momentum are the conjugate pairs. So the angular momentum is related to the magnetic orientation of things, and the angle is related to like what physical direction is it pointing in. Okay.
Okay. Well, I think we're sort of running out of time. So, I think everybody should give our wonderful speaker a round of applause, or virtual applause, as the case may be.